All right, hello everyone. So in my classes today, especially in the 8 a.m. class, we didn't get to do all of the examples I had planned, and I said I would make a short supplementary video. So I'm going to try and keep this video between 10 and 15 minutes. And so what we learned today is that we learned that some functions, so let's say we have a function from, let's just do an example, say we have a function from R3 to R4, right? And so imagine we know something about that function. Imagine we know it has a special property called being a linear function, right? So again, there was that definition that said that if we added two inputs, that was going to be the same as adding the outputs. And if we multiplied any input by any scalar, like 7 or 8 or 9 or c, that was going to be the same as this. Okay? So that was our definition of what a linear function was. And what we learned at the end of class was a theorem that says if we know, it says t is always given by a matrix. And that matrix, how do I figure out that matrix? Well, I take a matrix, I draw the brackets, and what I do is I apply that vector to E1, to E2, to E3, and I stop once I run out of those. And so let's think about what those are. So what am I doing? I'm taking E1, E2, E3. Well, those are inputs to my function. Right? I've got to plug those into T. So those had better be in my domain, right? So my domain is R3. And so what is E1? Well, E1 is the one that has first coordinate. E2 is the one that has second coordinate 1. And E3 is the one that has third coordinate 1. And so what I do, if I want to figure out what this matrix is, I just have to know what those three values are. Okay? And so let's do a problem with that. So let's say that we were given that t from R3 to R4 is linear, and t of E1, t of E2, t of E3 are equal to, and suppose I just told you what they were, right? This is some problem in the book. You know, I just tell you that these are the vectors, right? Maybe it looks like that. Maybe you're given that data. So this is all just what you're given. Then t is determined, t is just multiplication by a matrix A, where A is, well, what do? I take the first, I take t of E1, and I put that here. I take t of E2, and I take t of E3. And let's just do that. Some random matrix, but that is going to be the matrix that gives that linear transformation. Okay? And so if we're given this sort of data, that's how we put these pieces together. Right? And let's just check, right? Let's just check. We know that t of E1 is supposed to be 1, 2, 0, 1. Well, let's just try it. Let's just multiply A times the vector 1, 0, 0, 0, which is E1. Oops, sorry. The vector, sorry, I put an extra 0. Right? And so let's try it. If I do that, let's take our matrix A, copy, paste. If I do this and I multiply by 1, 0, 0, well, this is a really easy computation to do because I only have one non-zero entry. So that's going to be 1 times this first column, and then zeros times the other columns. So of course that's just going to be 1, 2, 0, 1, which hopefully is what we were given in the problem, and it is. Okay? So this process works for any linear transformation. And now we're going to apply that to some geometrical settings, right? So the following types of functions are linear. So this is something that we're going to use. And these are functions that have geometric descriptions. So any sort of rotation through the origin, maybe it's better to say about the origin, rotation about the origin, reflection through a line through the origin, any scaling or scaling by a constant. And the other main one that we might talk about is maybe projection onto a line through the origin. Now we could spend a whole semester just trying to understand geometry and different types of transformations. Mainly we're doing this to get practice thinking about linear transformations and ultimately about matrix multiplication next week. And so let's just do some of these examples, right? So let's say that t is rotation by, let's do 45 degrees. Clockwise, and we're operating on the plane. So I think I drew that way. I meant counterclockwise, so I meant the direction that I went. And so how do I find the matrix for t? Well, what do I need to do? Well, I need to find where t sends E1 and where t sends E2. And what is my picture? Well, E1 is the vector 1, 0. So that's here. So here's E1. Here's E2. And I didn't draw that to scale, did I? So let me draw it a little bit here. So this is a vector 1, 0. This is a vector 0, 1. This is E2. And what am I going to do is I'm going to rotate the plane by 45 degrees. And so where does this vector E1 go? It's going to go up here. Right? We got to figure out, well, man, what are the coordinates of that point? Okay, we'll do that in a second. And then where does the second vector go? Well, it also gets rotated 45 degrees. So it's going to go over here. Okay? And so I need to find the coordinates of those points. Right? And that I can just do with some trigonometry. Right? So I know that this vector had length 1. And so that means after I move it, I didn't change the length, I just rotated it. And so if I think about this triangle here, this has 45 degrees. And so this point, if I think about its x and y coordinates, the x coordinate should be root 2 over 2. The y coordinate should be root 2 over 2. Okay. Right. And similarly over here, the coordinate of this point is negative root 2 over 2. And the y coordinate is root 2 over 2. So go ahead and pause the video if you're confused as to what's going on there. It's just really a trig problem. So if you have a 45 triangle, you know the hypotenuse is 1. I just want you to work out kind of what the x coordinate and the y coordinate of that point should be. Okay. And so what did we see? We saw that that first vector got sent to this value, and the second vector got sent to this value. And so the matrix for t is, I just put the first vector in and then the second vector. So that's how I do that. So we're going to do 2 more examples, and then I think I'll stop. I want to keep this under 15 minutes. But in all of these examples, all we're doing is we're tracing where E1 and E2 are going to go. And so let's T be the transformation. And this is going to be a little bit more complicated. This is first rotate 90 degrees counterclockwise, then scale by a factor of 2, and then I'm going to do something crazy, and then reflect across the x-axis. In fact, it'll be a little bit easier actually if I do something a little bit more complicated. Across the line, y equals x. Right? Now I know this is a couple steps more complicated than before, but I want to show that it's the same process no matter what we do. And so T is a transformation from R2 to R2. And so we just need to do that picture. We need to say what happens to my two basis vectors. So I have E1 and E2, right, the x-axis and the y-axis. And what I'm going to do, I'm going to make sure they're drawn to scale. And I'm just going to mentally, I'm going to perform that. And so let's say the first one, let's do it in blue. So I'm picturing my vector, and I'm imagining it's going on a journey. And first it's going to be rotated 90 degrees around the origin. And then I'm going to scale it by a factor of 2, so I'm going to make it twice as long. And then I'm going to reflect it across this line y equals x. I better draw that line in. That seems relevant. Okay, let's do it. So I'm starting with my vector, and I'm going to first I'm going to rotate 90 degrees. So now I'm up here. Got a layover, and now I'm going to scale by a factor of 2. So go up here. And now I'm going to reflect it across the line y equals x. And so if you imagine I picked up this, if this was a piece of paper instead of an iPad, and I folded it over. If I folded it over, this vector would wind up down here. But if I fold it over, it's going to just shoot right through, and it's going to wind up out there. Okay? And so at the end of the day, it's going to wind up here. And what are the coordinates at that point? It's 2, 0. Right? Again, you may need to pause the video and just really work this out for yourself to kind of see that that's where it goes. But we've just seen that T of E1 happens to go to 2, 0. And now let's do the same thing for E2. Where does it go? Okay, well, let's start with our vector E2. Okay, first we're going to rotate 90 degrees, so now we're over here. Then we're going to scale by a factor of 2, so now we're out here. And now we're going to flip across that line. And what's going to happen is that it's going to get flipped, it's going to be shot right through that when we reflect it. It's like folding that paper over. We're going to wind up down here at the point 0, -2. Okay? And so T of E2 is equal to 0, -2. And so the matrix for A, for this transformation T, is going to be A. What do? We just put the two vectors in, the first vector and the second vector. Okay. All right. And so we'll do one more. I think we're approaching the 15-minute mark. So I'll just do one more example. And let's just say that T is projection onto the y-axis. I think you had a homework problem that was about that. And so what's happening pictorially is that if you have any vector, like say a vector over here, what's going to happen is it's going to get squished. It's going to be sent down like a movie projector. It's going to project it onto this y-axis. So this vector here would get sent down to this vector up here. Okay? And so if we think about coordinates, if this point had coordinates x, y, where would it wind up? Well, it would wind up at 0, y. Okay? And so let's do our handy dandy trick. how do? We have to figure out what t does to E1 and what t does to E2. And so let's just do it really quickly. So where does E1 going to go? Well, if I map that over, it's going to go to 0. It's just going to get thrown into 0. And where does E2 go? Well, E2 is in here. Where does E2 go? Well, it stays put. It's already on the y-axis. So it's just going to go to itself, which is 0, 1. And so our matrix for this transformation is going to be 0, 0, 0, 1. And let's just check. Is it true that if I multiply by xy, I get what we decided, that that projection is going to just kill what's in the x coordinate and make that 0, and it's going to preserve that y coordinate. Right? Let's just try it. 0, 0, 0, 1. If I do that multiplication, I do indeed get 0, y. So that's a verification that this process works. So thank you for watching. Again, my apologies that the 8 a.m. section did not go so well this morning.